having got introduced to certain kinds of forces, drawing free body diagrams, certain kinds of elements, wedge, string, etc., I'm going to get you introduced to yet another element called the spring element. The spring element, which is part and parcel of mechanical systems. Let's try and get some basic understanding of the spring element. All right. So, what's a spring according to you? What's a spring? These are properties of a spring. But what's a spring? Elastic comes later. Coil, it need not be a coil. Don't think that a spring is a coil. A spring element is one that can get deformed. But what is the springing action? It could get deformed, all right, but is capable of coming back to its original state, its original dimensions, original shape and size. That's a spring. Something that could get deformed under the influence of a set of balance forces, something that could get deformed under the influence of a set of balance forces, but could come back to its original shape, size, dimensions once it's allowed to do so. That's a spring. The platform on which I'm standing is a spring. It is getting deformed. It is getting deformed. This table is a spring. You don't realize, but it is getting deformed under the influence of, let's say, the weight of the books, etc. Even though the deformation could be small, it's anyways there. So a spring element essentially is an element, one that could get deformed under the influence of forces, but is capable of getting restored to its original dimensions, shape and size. That's a spring element. All right. Now, the conventional spring element that we are talking of, is set of strands, coils, a helical spring. This is a helical spring. The spring that you know of is what's called a helical spring. The trajectory of these strands is a helix. The trajectory of these strands, these strands these coils that you're seeing, they are these strands, they constitute what's called a helix. That shape is a helix. And this spring is called a helical spring. The spring is called a helical spring. We will, to begin with, deal with massless springs. Springs that are light. We will deal with massless springs or springs that are light in our initial stages of discussion. Light springs. A spring has what is referred to as a natural length of the spring. There is a natural or the undeformed length of the spring. L0 is a natural or the undeformed length of the spring. This is the natural length of the spring, undeformed length of the spring. And the spring could be compressed, the spring could be elongated, right? When I apply a force like this at this end of the spring, say at the end P, if I apply a force F, then the spring gets elongated. The spring gets elongated. This is the original position of P. Under the influence of a force F, this P comes to this point, P prime. PP prime is the elongation produced in the spring. PP prime is the elongation produced in the spring. Let's say when an externally applied force F is there, the spring gets elongated, for example. Now, this spring, if there is an external agent pulling the spring to the right like this, then the spring will exert on the external agent a force like this. The spring force would be like this. This is the force of an external agent. The spring at this end will apply on the external agent a spring force like this, a spring force like this. And the direction of the spring force at a given point, this is the spring force at the point P prime. The direction of the spring force would be such so as to try and restore the spring to its original state. Isn't it? P prime would have liked to be here because that represents the original state of the spring. So the spring force would act in a direction commensurate with the fact that it would want to get restored to its original state. So if the spring is elongated, the spring force at this point would act in this direction, Yes or no? In contrast, say, if this is the spring, this was the point P representing the natural state of the spring, and if someone happened to apply a force F like this at the point P, if someone happened to apply a force F at the point P like this, then the point P will come to this state P prime, right? The point P will come to the state P prime. And the spring, then we say, has got compressed. The spring has got compressed. Right? In this case, at P prime, however, the spring force will act to the right. When you compress the spring, it would want to expand so that it could come back to P. So then the spring force at P prime would act this way. It would want to spring back. The spring wants to spring back. If you elongate the spring, it would want to do this, as you can see. If you elongate the spring force will act to the left. If you compress the spring force will act to the right, so that the spring could get back to its natural or undeformed state. Right? That's a springing action in a spring. Okay?
So how is spring force different from tension?
No. First of all, both are forces. It's just the nomenclature assigned. When we talk of tension, the element that we connect with tension are these strings. The force in springs are not called tension, but you could call them tension as well. Spring force could be called tension at a given point in a spring. There is nothing that stops you from saying that, right? But generally, we talk of force in a spring, or when we talk of tension at a point in a spring, we talk of the spring force. That is what is meant, right? So the spring force at a given point acts in a direction so that the spring could get restored to its original state, original undeformed state. That's the whole idea, isn't it? Now, in a light spring, a spring that is light, just like in a light inextensible cord, the tension is the same at every point. In an ideal spring, a light ideal spring, the tension or the spring force is going to be the same at every point of the spring. That's important to understand, right? Now, having said this, let me take you to some more important aspects of the spring. These strands that you see, you know, these strands, if you cut a strand like this, then there is going to be a cross-sectional area. There is going to be a cross-sectional area of these strands, isn't it? It's like a coiled wire. And if you cut this wire, you see a cross-section gets exposed. If you cut it like this and view from here, you see, let's say, a circular cross-section of the wire, right? That's area of cross-section of the spring. That's area of cross-section of the spring. So the spring has an area of cross section A, say. These coiled strands, they have an area of cross section A. This force F is acting perpendicular to this area A. This force F is acting perpendicular to this area A of these strands. So this is this view of the cross section. I see, when I view the cross section like this, I see a circle like this. And F is acting spread over an area A. F is acting spread over an area A. F is the force acting on the cross section A, on the cross section A, right? Now, if F is the force acting on the cross section A, then we define what is called the stress acting on the spring. The stress acting over this cross section is defined as the force per unit area, is defined as the force per unit area. That's defined as the stress, Newton per meter squared. That's the stress acting over this area of cross section A. Now, because of this externally applied force, let's say this point P goes from P to P prime. And the spring gets elongated by an amount x. The spring gets elongated by an amount x. L0 was the original length of the spring. L0 was the original length of the spring. Then we define what is called the strain produced in the spring. Strain produced in the spring is defined as change in length divided by the original length. Strain is defined as change in length x divided by the original length L0. That's the strain, x divided by L0. Now it has been found that the ratio of stress to strain will be a constant. Ratio of stress to strain will be a constant. If I vary F, x will vary. If I vary F, x will vary, but stress by strain will remain constant. Ratio of stress to strain is found to be a constant. And this constant will depend on the property of the material of which the spring is made of. This constant will not depend on the geometry of the spring. It will only depend on the property of the material of which the spring is made of. That means the spring could have been made of steel, could have been made of copper, could have been made of aluminum, and so on and so forth. This constant will only depend on the material of which the spring is made of. Depends on the material of the spring. Iron or steel or copper, aluminum, so on and so forth, right? And this property is commonly referred to as Y, the Young's modulus of the material. It's called the Young's modulus of the material. Young's modulus of the material. Why? It measures the elastic properties of the material. It measures the elastic properties of the material, and it is documented. The Y would be known for different materials, copper, steel, aluminum, and so on and so forth. For different materials, this value Y is documented, would be a known entity. Okay. Now, and it's also called the modulus of elasticity. It's also referred to as modulus of elasticity. Modulus of elasticity or Young's modulus. It measures what we will commonly refer to as the elastic properties of the material, the elastic properties of the material. Now, so stress, like I said, is force per unit cross-sectional area, force acting on the spring per unit cross-sectional area, divided by strain. Strain is change in length divided by L naught. X is the change in length when a force F is applied, when the stress is F by A. So X divided by L naught, that must be Y. That must be Y, yes or no? Right? So we then have the force F as AY by L naught into X. AY by L naught into X, that's what we have. Yes or no? Right? This F is AY by L naught into X is what we get. What's the confusion? L naught is the original length of the spring, natural undeformed length of the spring. The length of the spring in its natural state. Yes, somebody else was invoking a question. Yes, please tell me. Really? Really? Check your algebra. This will be X by L naught into Y. And this A will go up. God bless you. That's all right. Don't worry about it. Yes or no? That means on a spring with area of cross section A and natural length L naught and with modulus of elasticity Y, in order to produce a deformation X in the spring, change in length, a force F must be applied. Where F is given by AY by L naught into X. This F, when applied on the spring, will produce a deformation to the extent of X units. It could be a force which is elongating the spring. It could be a force which is compressing the spring. Yes or no? Now, when I talk of a given spring, so far so good. Is that okay or not okay? Right? Now if I talk of a given spring, F is AY by L naught into X. Now, for a given spring, A is the area of cross section of its strands. L naught is the natural length of the spring, right? So A and L naught are related to the geometry, the area of cross section of these strands, and L naught the natural length of the spring. Where Y is not related to the geometry, Y is related to the material of which the spring is made of, right? So this factor AY by L naught depends on two things. What are the two things? One is geometry of which the spring is made of. Geometry of the spring, that means area of cross section in an L naught, and material of the spring. Geometry is about area of cross section and the natural length, whereas material is about Y, the Young's modulus of the material of which the spring is made of. Right? And commonly, this number AY by L naught is designated by K, which is called the spring constant. Spring constant of the spring. Sometimes they also call it stiffness constant. Stiffness constant. Which is AY by L naught. Yes or no? So the force required to cause a deformation X is given by K into X. The force required to cause a deformation X in an ideal spring is proportional to x. In an ideal spring is proportional to x. This is the characteristic of an ideal spring. Force required to deform it by an amount x is proportional to x. Yes or no? Right? Where k is a constant depending on two things, geometry of the spring and material of the spring. When it's about geometry, we talk of area of cross section and length. When it's material, we talk of y, the Young's modulus. Yes or no? Right? Very clearly, the greater the value of k, the greater the value of k, the greater would be the force required to deform it by an amount x. Yes or no? The greater the value of k, the greater would be the force required to deform it by an amount x. Right? And therefore it measures what is called the stiffness of the spring. The greater the value of k, the greater is the stiffness in the spring, and the greater would be the force required for a given deformation x. Right? Force constant, it's sometimes also called force constant. It's also called force constant, spring constant, or stiffness constant. Non-ideal springs don't show this linear behavior. Force is not directly proportional to the elongation or deformation produced in the spring. And this x could be elongation as well as compression in the spring. Does not matter. This x is the change over and above its natural length. Whatever difference you see between the actual length and the natural length, that is x. That is x. That's the deformation in the spring. Compression or elongation. So, this linear behavior is exhibited by springs that are called ideal springs. Such springs are called ideal springs. An ideal spring is not about being light. An ideal spring is about one in which the deformation is proportional to the externally applied force. An ideal spring may or may not be light. But as of now, we'll talk of ideal springs that are light. Consequently, if ideal springs that are light, then the spring force would be the same at every point of the spring in a light. So, the fact that at every point the spring force is the same is a consequence of the spring being light. The fact that displacement and force are proportional, the compression or elongation is proportional to the applied force, is a consequence of what is referred to as an ideal spring. And this rule is called, this law is called Hooke's law. This law is called Hooke's law. Hooke's law. Clear? Now, so far so good, right? Now suppose there is a spring. This is a spring, say AB is a spring, okay, and its area of cross section is A, its natural length is, so let me call PQ because A I refer to as area of cross section. So PQ is a spring, say, of area of cross section of the strands A, and L naught the natural length, and Y the Young's modulus of the material of which the spring is made of, right? Then, like I said, the stiffness constant or the spring constant or the force constant of the spring is given by AY by L naught, right? Now, for a given spring, Y will not change. Area of cross section, area of these strands, that's not going to change, right? So say A into Y will be a constant, let's say, for a given spring, right? If A is the same, Y is the same, then you see that K is inversely proportional to L naught. K is inversely proportional to L naught. That means if L naught is halved, then K gets doubled. That means now if I break the spring into two springs, PP prime and QQ prime, two identical lengths, L naught by 2 and L naught by 2. Suppose I cut the spring into two identical springs, L naught by 2 and L naught by 2. Do you realize the A is the same as the A here? The Y is the same as the Y there, same material, right? But if L naught is halved, K gets doubled. So if K was the force constant of the mother spring, then the force constant of the constituents would be 2K and 2K. Yes or no? Because if L is halved, K gets doubled. So if this had original K, then this would have force constant, spring constant, stiffness constant, 2K, 2K. If I break it up into 3 equal parts, then 3K, 3K, 3K would be the force constant of each part. Yes or no? If I break it up into n equal lengths, then nk, nk, nk of each of the lengths. Yes or no? Clear? That's why, see, a smaller length will resist change in deformation more. The greater the value of stiffness constant, greater is its resistance to change of length. Right? So, smaller lengths will resist change in dimensions, smaller lengths will resist change in dimensions more than bigger lengths. So, smaller lengths have greater stiffness constants, other things remaining the same. Isn't it? Chotto lonka boddo jhal. Right? So, this has greater stiffness constant compared to this. Yes or no? Now, having said this, shall I proceed? Let me tell you combination of springs, right? Springs with different spring constants connected in various ways. Let me deal with that, okay? Springs with different spring constants or stiffness constants connected in 2 basic ways. Can I wipe this off? Gajada, protein missed you, yaar. I don't know. WTF or not, you would know best, but he missed you, yaar. We'll talk about that later. Otherwise, he'll spring into action. No, that's all right. All in a lighter vein. What's happening? Yeah, what is happening? We'll talk about it in a little while. Let me. We'll talk about it. Let me take care of some academic activities first before we get into non-academic action, right? Don't worry, I have so many ways to counter the wrath on your face. You would be set to ground state in a few minutes from now. Trust me. Now, see, if I have 2 springs, one with force constant K1, another with force constant K2. Connected end to end. Connected end to end. All right. When this happens, we say that these 2 springs are in series. We say these 2 springs are in series. These are springs in series. Now, when I apply a force F, say when I apply a force F on the spring, then the spring under the influence of this force gets elongated by an amount x. the spring under the influence of this force gets elongated by a total amount x. And let's say this spring got elongated by an amount x1 and this spring got elongated by an amount x2. The total elongation was x, which was x1 plus x2. Part of x came out of x1, the rest came out of x2. So the total elongation produced in the spring was x1 plus x2. x1 the elongation in one spring, x2 the elongation in the other spring. Now, if x1 is the elongation in this spring, then the spring force here must be k1 x1 in the spring, right? The spring force here must have been k2 x2, the force in the spring, right? And do you realize that k1 x1 must be equal to k2 x2? It's a single spring, so the light, the entire entity is light, so at every point the spring force is going to be the same. So k1 x1 must be equal to k2 x2, yes or no, right? Now, I want to replace this spring by one single spring. When I say I want to replace the spring by one single spring, which means, let's say that equivalent spring has force constant k, spring constant k. Now, if this combination is equivalent to this single spring, what it means is that when I apply the same force F on this equivalent spring, the same deformation x results. The same deformation x results. This is what it means. If this combination is equivalent to this single spring of equivalent spring constant k, what it means is that when I apply the same force on this, then the same deformation x results in this spring. This is what it means. That means if k is the equivalent spring constant of this combination is replaced by one single spring of spring constant k, then very clearly F would be k into x. F would be k into x. The spring force here is going to be k into x, isn't it? Now, this x then can be replaced by f by k, and all of this will be f. F will be k1 x1 is k2 x2, the spring force. Eventually, why is the spring force same as f when it gets deformed by an amount x? See, when I keep pulling the spring, okay, this force F remains the same. But at some point of time, why does it stop getting deformed? Because the spring force balances the externally applied force F. So, when the spring reaches its total elongation x that could have been produced by F, then the spring force F is the same as F, the externally applied force. Right? So F, which is not just the externally applied force, is also the spring force at every point. K1 x1 and K2 x2 and so on and so forth. Yes or no? Of course. See, when I pull the spring, initially when I have started to pull the spring is undeformed. The spring now builds up deformation. It grows in length, right? And the spring force increases. The spring force initially increases. The spring force is acting like this. Initially it was 0. Initially the spring force was 0. Eventually what happens is, when I elongate it by an amount x, then the spring force just balances F. And F is the force which has caused a deformation x. So this F is kx, which is also the spring force, right? And the spring force, since this has got deformed by an amount x1, the spring force here is k1 x1, the spring force here is k2 x2, and all of them must be equal to F, the spring force at every point of the spring, right? For an equivalent spring, when I apply a force F to the right, the spring gets deformed by an amount x. This is the equivalent spring. So the same force will cause the same amount of deformation x. So x can be replaced by F by k here. X can be replaced by F by k. X1 can be replaced by F by k1. X2 can be replaced by F by k2. Yes or no? Which means 1 by k is 1 by K1 plus 1 by K2. If two springs of spring constants K1 and K2 are connected in series, the equivalent spring constant is given by 1 by K is 1 by K1 plus 1 by K2. Right? So springs in series are like resistors in parallel. Right? If there are n springs, then 1 by K would be 1 by K1 plus 1 by K2 plus 1 by K3 plus 1 by Kn. Yes or no? Right? That's the story of springs in series. Now, let's look at what is referred to as springs in parallel. Can I wipe this off? So, say this is a fixed wall. This is a spring with force constant K1. This is another spring with force constant K2. And say there is a small diaphragm with which I connect these two springs. Okay? PQ. Now, I apply a force F like this. On this diaphragm, I apply a force F like this. And consequently, both the springs, see the diaphragm is moving horizontally, so the deformation in both the springs would be the same. So, eventually, P comes to P prime, Q comes to Q prime. Right? And the spring, both the springs would have got deformed to the tune of x units. Clear? Now, so the springs come to this point. This is the externally applied force. Now, notice that this is one spring. It has got deformed by an amount x. So the spring force here would act in this direction, because the spring force is always a restoring force. So the spring force at P prime will act like this and will be K1 into x. The spring force at Q prime would act like this and would be K2 into x. Would be the spring force here. Yes or no? And this diaphragm is an equilibrium. On this diaphragm, there is F acting to the right and the spring force K1x and K2x acting to the left. Under the influence of these two, then the diaphragm is in equilibrium eventually. So F must be equal to K1x plus K2x. That's the story of the diaphragm in equilibrium. Clear? Now, what I want to do is, I want to replace these two springs in parallel by one single spring, the equivalent spring, having force constant K, and when I apply a force F on this spring gets elongated by an amount x. Right? So this F must be Kx in the equivalent spring. Equivalence means when I apply the same force F, the same kind of deformation results. That's when this system is equivalent to this system. You know what I'm saying? So, this F is also Kx, where K is the force constant of the equivalent spring. So, this is K into x. Right? Or K then turns out to be K1 plus K2. K then turns out to be K1 plus K2. So, if two springs are in parallel, they could be replaced by one single spring whose force constant or spring constant would be sum of these spring constants. Yes or no? So, springs in parallel are like resistors in series. If there are n springs in parallel, then they could be replaced by one single spring with force constant K, which is K1 plus K2 plus K3 plus Kn. That's the story. Got me? Now, so far so good, not a problem. One important characteristic of a spring, one very important characteristic of a spring. Can I wipe this off? If say this is a spring and let's say I connect a block M at the end of a spring. Say this spring was already elongated by an amount x. The spring was already elongated by an amount x. L naught was its original length. And this block M is connected at this end. Right? And so what would be the spring force? Kx. Right? And will it be to the left or to the right? Left, because it's elongated. This is the state that the spring would want to come to. So at this point, the spring force on the mass will be Kx to the left. The spring force on the mass would be Kx to the left. Yes or no? No? Now, when for some reason I apply an impulse on this mass J. An impulse is like a force applied for a short time, for example. Force into the small time for which it's applied, that's an impulse. That's an impulse. So, let's say I hit it with a billiard stick. I hit it with a billiard stick, right? With an impulse J. Then, even though there is an abrupt action on the mass M, there is an abrupt action on the mass M, the spring force does not abruptly change in value. The spring force, which is Kx, does not abruptly change in value. The spring force was Kx before the impulse, and right after the impulse also it remains Kx. If at all it will change over a period of time. The spring force, we say in principle, is non-impulsive. The spring is a non-impulsive element. The spring is what is referred to as a non-impulsive element. Now, it's another story that, I cut the spring here. Now, you're killing the spring. Then, of course, the spring force will reduce to zero. But if I'm not cutting the spring, I'm, applying some forces here and there, directly or indirectly to the spring, then the spring force is not going to change abruptly. Just before and just after an action, the spring force will remain preserved, right? That property of the spring is called a non-impulsive property. Non-impulsive property. In strings, a string is a impulsive element. For example, if this is a string, and there is a block of mass M here, right? And the string is taut. The string is, say, taut. And there is a particle of mass small m that falls on this block with a velocity v. Then this tension T that was there in the string before the mass fell, and the tension right after the impact, there is an impact because of this mass fall, is going to be different. The tension in string can act impulsively, will change abruptly, but the forces in springs will not change abruptly, I mean, if I were to give this mass, suddenly give this mass a velocity v naught to the right, the spring force is going to change over a period of time, but not right after an action. So it's non-impulsive. It doesn't change over an instant. Whereas string is impulsive. Tension in the string can change abruptly. abruptly, whereas force in the spring cannot change abruptly. That's why a string is called an impulsive element, whereas a spring is called a non-impulsive entity. A spring is non-impulsive. A spring is non-impulsive. String is impulsive. Now, to give you an example, can I wipe this off? Say there is a support there is a mass m1 here, there is a mass m2 here, and the spring is compressed. There is a spring here of force constant K. There is a spring here with force constant K. Obviously, you know, this mass m2 would have compressed the spring. Would have compressed the spring, and the system is in equilibrium, say. Let's say the system is in equilibrium. The spring is compressed. The spring is compressed. Let me first find out the extent to which the spring is compressed. Let me first find out the extent to which the spring is compressed. When it's in equilibrium, Say the spring is compressed by an amount x. Let me draw the free body diagram of M2. Let me draw the free body diagram of M2. What are the forces acting on M2? There is M2G acting downwards. There is M2G acting downwards. And the spring is compressed. So the spring force will act on this mass upwards. Yes or no? If you compress the spring like this, then the spring force on M2 will act upwards. And if the spring is compressed by an amount x, then the spring force is going to be kx upwards. Yes or no? It's going to be kx upwards on this mass. If you look at M1, free body diagram of M1, M1 would be M1G downwards, right? See, a compressed spring would want to open up, So, the spring force on M1, see, the spring is wanting to open up. So, the spring force on M1 is going to be downwards and is going to be kx downwards. The spring force is going to be kx downwards, right? And the support on which it is resting, let's say that support will exert on M1 a normal reaction R like this. A normal reaction R like this. If I compress the spring like this, I've compressed the spring, right? I've compressed the spring. This was the original state of the spring. See, this end should have been here. I've compressed it like this. Will the spring force not act upwards on mass M2? You know? Isn't it? A compressed spring would want to open up. An elongated spring would want to cave in. This is what they want to do, right? So do you all... This is a spring, okay, and it's compressed. It's compressed. This is the spring, original length, and it's compressed. It would want to open up, isn't it? Now, if it wants to open up at this end, it would exert a force upwards, and at this end, it would want to exert a force downwards because it is trying to do this. So at the upper end, it will exert a force upwards. At the lower end, it would want to exert a force downwards. This is what the spring wants to do. A compressed spring, right? This is a compressed spring. It would want to do this. Right? So at the upper end, it would want to exert a force like this. At the lower end, it would want to exert a force in the downward direction. Yes or no? Right? Now tell me this. In equilibrium, this is the free body diagram of M2 and M1. Now what happens if I suddenly withdraw the support? What happens when I suddenly abruptly withdraw the support? When I abruptly withdraw the support, the spring force will not change abruptly because it's a non-impulsive element. The spring is a non-impulsive element. So the spring force will still remain kx right after withdrawal of the support. Right? R will become 0. R will become 0. Right? Now in this case, do you realize M2G was in equilibrium? So kx must have been equal to M2G before I withdrew, and right after I withdrew, this fact will not change. M2G and kx will still balance each other. That means right after withdrawal of the support, this will still be in equilibrium. Net force on M2 would be 0. So acceleration of M2, A2 would be 0. Right after withdrawal of the support, acceleration of M2 would be 0. But look at M1. Look at M1. So once I withdraw the support, see, when the support was there, the support was exerting a normal reaction on M1 and M1 was in equilibrium. So R was balancing Kx plus M1G. Yes or no? This is what R was doing. Before I withdrew the support, say when the support was there. And this was also in equilibrium. This was M1. So weight M2, M2G was being balanced by upward spring force. This was in equilibrium before I withdrew the support. Such was the compression produced in the spring so that it could balance M2G. So far so good. And the free body diagram of M1 was like this, right? Now when I withdraw the support, I told you the spring is a non-impulsive element. The spring force right after withdrawal will still remain Kx, right? This R will become 0, this R will become 0, right? And what would be the forces acting on M2? M2G still downwards, Kx still upwards, and Kx was balancing M2G, so the net force on M2 is 0, isn't it? Because M2G downwards and Kx upwards. Net force is 0. If the net force is 0, what is the acceleration of M2? 0, right? A2 is 0. But look at M1. Look at M1. The net force now, if R is withdrawn, then the net force is downwards. Kx plus M1G is the net force acting downwards on M1. Yes or no? That's a net force acting on M1 downwards. But what is Kx? Kx is M2G. So Kx is M2G. So M2 plus M1 into G. That's a net downward force acting on M1. So what would be the acceleration of M1? This force divided by mass. So M2 plus M1 into G divided by M1. That will be the acceleration of M1 downwards right after I withdrew the support. Yes or no? Are you all okay with this? Do you understand the implication of its non-impulsive character? Kx did not change. R went into oblivion because contact was lost. Weight anyway is non-impulsive. Weight anyways is a constant, right? That's not going to change. So acceleration right after withdrawal of the support, acceleration of this was 0, whereas acceleration of this mass was this. Can I give you another problem to solve? Then of course that will change. This is just before and just after. All that I'm trying to illustrate here is that it is non-impulsive. It will not act right before and right after. That's all that I'm saying here. It will change. Now over a period of time, there are unbalanced forces and the spring force will change. The elongation in the spring will change. This has an acceleration, this has a non-zero acceleration. The spring will now elongate and spring force will change, but not in 0 seconds. In 0 seconds, the tension can change, but in 0 seconds, the spring force will not change. Say, first of all, it becomes important for us to find the elongation in various springs when the whole thing is in equilibrium. Say, this spring has elongated by an amount x1. Say, this spring has elongated by an amount x2. And say, this spring has elongated by an amount x3. All right, these are the three springs. Now, so in equilibrium, Let me find things in equilibrium, because right after I snap spring 2, that state will not change, at least for 1 and 3. For 2, of course, suddenly it will become 0, but for 1 and 3 it will remain preserved before and after snapping spring 2. Yes or no? Now, look at this spring. There is a spring force. See, the spring is elongated. The spring is elongated by an amount x3. It will exert on this mass m a spring force kx3, which will just about balance 3 mg. Yes or no? Which will just about balance 3 mg. What do you say? So I know kx3. That's 3 mg by drawing the free body diagram of this mass. Now, let me look at mass 2m. Let me look at mass 2m. So if I look at mass 2m, then there is 2 mg acting downwards, right? Now, at every point of the spring force will be kx3, and the spring is elongated. So if the spring is elongated, it would want to cave in. So it will exert kx3 downwards on 2m. So it will exert kx3 downwards on 2m. And this kx3 we have already found is 3 mg. And now this spring is also elongated. So it will exert on 2m a spring force kx2. A spring force kx2 will act on this. So kx2. Now, very clearly, this kx2 will take care of 2 mg plus 3 mg, that is 5 mg. So kx2 is 5 mg. So this also I know. Good for us. Right? Now let me look at this mass. Let me look at this mass m. There is mg downwards. Then there is going to be kx2 acting on it downwards. There is going to be kx2 acting on it downwards, right? But kx2 is 5 mg. So there is kx2 acting on it downwards, which is 5 mg. And then there is, this spring is elongated by an amount x1. So there is going to be kx1 acting upwards. Yes or no? So kx1 acting upwards. And this kx1 will take care of mg plus 5 mg, which is 6 mg. Yes or no? Right?
I mean, for finding the force acting on M, can we just consider the lower portions as a single system, and just since the springs are massless, just take it as 5, the acceleration downwards?
This part of the system, you could have done that. It'll add up. Not a problem. You could have done that. I mean, you could have looked at this free body, and this would be an internal force. No issues. That's a very good thing to do, actually. If you have done that, that's not bad. Right? So kx1 is 6 mg. Have you understood this? Yes.
Can you explain the free body diagram of 2m? So why is that?
This 2m?
Yes, why is kx3 acting downwards?
See, if this spring is elongated. See, imagine this spring to be elongated. So it would want to do this, right? The spring would want to do this. So if it would want to do this, it will exert a force on 3m upwards and a force on 2m downwards, isn't it? If a spring, so imagine this spring, it's elongated, right? What would this is the spring, right? So this spring would want to do this, it would want to do this, right? Therefore it will exert on the upper mass a force downwards, and on the lower mass a force upwards. Yes or no? Got me? Are you all okay with this? Right? Now, so does this calculation match with yours? Right? Now when I snap spring 2, what happens? See, suddenly I cut this. So, no existence. Then look at M. What are the forces? Will the spring force change abruptly? No. So what are the forces acting on it? mg downwards and kx1 upwards. But what is kx1? Kx1 we have found is 6 mg. So kx1 is 6 mg. That means the net force is 6 mg minus mg, which is 5 mg upwards. This 5 mg upwards will produce an upward acceleration 5g. Yes or no? 5 mg divided by mass would be 5g. So this mass would have an upward acceleration 5g. Do you understand that? Kx1, which is 6 mg minus mg, 5 mg divided by mass m would be 5g upwards. That's as far as this mass is concerned. Look at 2m. There is going to be on 2m 2mg downwards plus kx3 downwards. But what is kx3? Kx3 is 3mg. So the net downward force acting on it is 5mg. And this 5mg acting on mass 2m will produce a downward acceleration of 5g by 2. 5mg divided by 2m is 5g by 2. Yes or no? Of course, yes, I will. See, right after I snapped the spring, what are the forces acting on it? 2mg downwards. There was kx3 that was previously acting downwards on this. So 2mg plus kx3. 2mg plus kx3, isn't it? This, where did the mass, yeah. So then what would happen? This will go away, spring 2 is snapped. So what are the forces acting on mass 2m? 2mg plus kx3, which is 5mg. 5mg acting on mass 2m will produce an acceleration 5mg by 2m, which is 5g by 2. So the acceleration of this would be 5g by 2. Does it match with your calculations? Right. So the acceleration of 2m would be 5g downwards. Now look at 3m. Now what about 3m? 3m, the forces acting are on 3m, that is this mass, there is 3mg downwards. And then there is kx3 upwards. Kx3 upwards. 2m. So 5mg by 2m is 5g by 2, isn't it? That's all right. So on 3m, what are the forces acting? 3mg downwards and kx3 upwards. But kx3 is 3mg. What is the net force acting on 3m? 0. 3mg minus 3mg, net force 0. So what is the acceleration of this? 0. Right after snapping the spring, the acceleration of this is 0. The acceleration of this is 5g by 2 downwards. The acceleration of this is 5g upwards. Did you get the same things? Right? So you understand what it means by the non-impulsive attribute of a spring? Right?